Circular motion is not always uniform. We define circular motions as uniform when the speed is constant in the whole circle. But if we look at mechanisms like this, you will find out that the objects go through circular motions at different segments, but the speed is not constant at different places. The speed has different values. So, how do we solve problems with structures like that? These are rides where you get an energy here, and then when you that potential energy will be used to get into kinetic energy to go up. So, so let's look at an example where we have got an object here, and the object comes down, and then it goes through a circle, and then it comes down and go in this direction. So we want to find out the minimum height that we need to roll that object down from so that it will go through the circular motion and it will not fall from here. So it will be able to go and complete the cycle and come here. So how do we do it? We won't be able to use the equations that we used before because at different places, at different segments, the object is going through different types of motions. So obviously, there's a circular motion here, but not here. So how do we solve that? If we use the law of conservation of energy, that we know that this object has some potential energy here, and that energy will be converted into kinetic energy, and that will have some velocity. That velocity and that kinetic energy is the one that will be used to go to this location, and from that position that object will get some more kinetic energy, and that object will be moving down and go through this path. So so let's use the law of conservation of energy at different places, at different points, to find the minimum height from which we have to drop that object from. Because in case if we drop the object less than h, it may not reach here, or it may not just go there and falls off. So what we are going to do is that the forces acting at different positions, like here we have the weight acting this way and the reaction or the normal force acting this way, and here we have the weight acting this way and the normal force acting on the same direction. So if there's no normal force, that means the object is not in touch with that. So we are going to find um, the minimum height by using the limit value, that is when t is 0. We're actually going to use n for the normal force instead of t. That makes sense. So we are going to find um, the minimum height by having n as 0. So let's write the equations. So the kinetic energy here at this point is Ka, and the potential energy is Ua, and the kinetic energy here is Kb, and here is Ub. So if you use the conservation of energy, the energy here is same as here. So what is Ka? So, Ka is equal to 0, because there's no velocity for that object at A, and UA is equal to mgh, because that's the potential energy at height. Now kv, let's say the velocity is v, so it's half mv squared, and ub, what's the potential energy there? Because the radius of the circle is r, so the height is 2r, so mg times 2r. So we can write it as 2 mgr. So Ka plus Ua is equal to Kb plus Ub. So mgh is equal to half mv squared plus 2mgr. So if we cancel m here and here, so what we will get is gh is equal to v squared divided by 2 plus 2gr. So that's equation 1. And now what we are going to do is we are going to use the circular motion equation at point B, which is the net uh, force is equal to the mass time acceleration. So at that point B, the net force is only mg because n is 0. So let's write that down. So at B, n is 0. That means mg, that's the total net force, is equal to mv squared over. That means we get an equation here, v squared is equal to rg. So that's the second equation. So from equation 1 and 2, if we substitute what we have got the value for v squared in equation 1, we get gh is equal to v squared. We are going to put rg divided by 2 plus 2gr. Now g is going to cancel each other, so we will get h is equal to r by 2 plus 2r. So that's quite an interesting one. So h is, so r by 2, that's the 4r, so 5r divided by 2. So that's the answer. So what we conclude from this is the height should be the height should be above 2.5 r, which is the radius of the circle, for the object to go through the circular motion and come back here safely and continue the journey. So this could be a fun ride for children to sit in these cubicles and go this way and go up and come here. So when they design these structures, they look through all these things, and they have to use the conservation of energy formulas to calculate and find out the velocity at different places, and to make sure whatever going here will be able to go up and come down. So the answer is h should be greater than 2.5 r. So this is another cart or a trolley that's going up here and coming down and going there and then going this way. So let's look at the forces acting on this object at different places. So the object is going through a circular motions at this segment, and there's another circular motion in this segment. So if we look at this place, the the net force, which is the force towards the center, is going to be N minus mg is equal to m v square over r. Here, the force towards the center is going to be mg minus n is equal to mv square over r. So what's happened to the n, which is the normal force? So in this case, the normal force is equal to mg plus mv square over r. So the normal force is greater than the weight of that object, and this place n is equal to mg minus mv square over r. So if you are sitting in this card, when it goes through this segment, at this place, the normal force is greater than the weight because normal force is equal to weight plus mv squared over r. So when you're in the car, you will feel heavier than your weight because the weight you feel is depending on the normal force. The normal force is bigger here. But when you go up here, the normal force is equal to mg minus mv squared over r. That means you will feel lighter than your real weight.